Hello, it's Keith here, and this is the second of the 68000 YQuest assembly programming tutorials. Today we're going to be looking at the x68000. We're going to be looking at the platform-specific code that handles YQuest on this system. Now, first of all, I'll just show you the game in action. If we just throw it up here. So here we go. So here is YQuest on the 68000. Now, it's configured to use joystick controls, but I've got them mapped to my keys here. And you can see the game is working nicely. Now, this version uses bitmap graphics. So we're not using the hardware sprites, but the bitmap graphics of the 68000 are very smooth anyway, so it doesn't really offer any disadvantages doing that, but we will be looking at a hardware sprite version later. The game has simple sound with the Chibi Sound driver I wrote in the past, and it's basically a perfect port of the game. So we're going to be looking at the code for this today, and we're going to learn more about it. So let's go over to the code and let's see what this game needed. Okay, so here's the code for today's example. First of all, we're defining the inclusion of some basic macros we're going to need and some parameters to define the size of the screen, and that this is for the multi-platform code because different systems use different size screens, and so depending on the screen size we need to change the logic of the code accordingly, so that's what that's for. Now here we've got the code that will turn on the graphics screen we're using the 16 color 256 by 256 screen here. So these are doing that. These are basically fixed values that you need to use. Now, if we were using hardware sprites, we'd need these. We're not using hardware sprites, so we don't need to use them. Now, then we're defining our palette. We've got our palette at the bottom of the file. Somewhere here it is. This is in the native format for the x68000. So this is 5 bits per channel here, green, red, blue, you can see. So these are the colors. And we're transferring those to the palette registers at E82000 onwards here. Okay, now after we've done that, we're then using this function CLDIR, which is one of my common functions, and this is going to write hexadecimal 800 bytes of zeros to the user RAM. Now the user RAM, where is it? Is just down here. This is some temporary memory for the variables of our game. So we're just clearing that out for the game to start, and the game will actually initialize its own values as the levels start and so on. So that's for all of the variables that the game uses. Now, next we're going to show the title screen. So the title screen starts here. We're first setting the number of lives to 3 because this is essentially starting a new game, zeroing the score, zeroing the level number, and also resetting the player object sprite. Now these are all held in user RAM, of course, and we're then also silencing the sound using Chibi Sound. Next, we're going to show the title screen. Now the title screen is that thing we saw earlier. That's this thing here. It's a bit slow. There it is. That's this. Now this is made up of all of the sprites in a form of a tile map. So what we're doing here is we're loading in from the title picture, which will be in the multi-platform code for this screen size. We're loading in an individual byte each time, and that is one tile, and then we're showing that to the screen with get sprite address, which calculates the memory address because the sprite bitmap data is within this file. It's calculating the address of that, and then it's showing it to the screen, provided it's not a zero. The zero tiles are not shown because they're the blank areas. So that's what that's doing there. It just shows each tile across the screen and then down the screen, filling the introduction screen. So we're just repeating until the entire thing's drawn there. Then we've got some text routines here to show various messages to the screen. Now the print string routines here are using a bitmap font. It's using a native format bitmap font and not the 1 bit per pixel one I've used in the past. And then we're going to start the game. Now at the start of each level, whether the first level or any other level, we wait for the fire to be pressed, clear the screen, recenter the player to the middle of the screen and give them some invincibility using this reset player function, and then we initialize the level data, the objects on the screen, the crystals, the mines, and any enemies. Okay, now next of all is the main loop. Now this is what's going to basically run for the vast majority of the game here. So what we're doing here is we've got a delay. We're going to set a default of no key presses, and then we're going to read in from the joystick, and we're going to have a look at that in a moment, and then we're going to see if any keys are pressed. Now, if a key isn't pressed, we're going to keep reading, but if a key is pressed, we store it for processing later on. Okay, well, let's take a look at that key reading routine, because that's quite important. Now, the key reading routine here is the one I've taken from my other tutorials, the platform-specific series. We're reading in from all of the joystick buttons, far more than we actually need. YQuest only uses 2 fire buttons. Now, if you remember, the x68000 has 2 potential ways of working with a joystick. It can use an MSX joystick, that's a 2-button joystick, or it can use a Sega 6-button joystick if it prefers. So we're actually loading in from the more advanced one here, even though we're not using all the controls. So we're only processing a single joystick here because we're not using 2 joysticks. We're loading the address of the joystick in here into A0, and then we are processing by selecting the port, and this selects which set of directions we're reading in, and we write that to E9A005, and then we move out from the address of the joystick, which in this case is E9A001. So we're then just shifting all the bits into the order that we want here. Now this port will give us up, down, left and right, then a blank, and then fires 1 and 2 here. So that's the first set. Now when we send this alternate code to E9A005 with bits 4 and 5 set to 1, we get 3, 4, 5, 6 mode and start here in a rather odd format there. And so again, we kind of need to shift some bits around to get those into the position we want. Okay, so this function here will effectively process one joystick, and this will effectively read in all of the directions of the joystick, and it will output them into this much neater format here, which is why there's all that bit shifting down there. Now that's going to read in our joystick controls, and that's what we're using here. And so then we're just checking if any of the bits are 0, and if any are, then a button's pressed, and we're going to process that later on. Now when we get here, we're basically drawing the user interface, the score and the lives and things in the corners. We're then clearing the old player object off the screen by loading the pointer to the player object into A4 and then running this function here. And then what we're doing is we're checking the key timeout. Now the game works by acceleration, so if we press up, we'll start moving up and we'll keep moving up in the constant direction. So if we hold up, we don't want to accelerate too fast, and that's what the key timeout's for. If the key timeout is not 0, then we're skipping over processing the directions. Processing the directions works like this. We've got the X acceleration and the Y acceleration here, and what we're doing is we're testing the bits in the joystick that we read in here with read control dual, and then we're testing each of the directions and we're altering the acceleration accordingly. So this will change our acceleration, and also we're setting the timeout for next time if one of the directions is pressed, and we're updating that here. Now if fire 1 is pressed, we're firing a bullet. If fire 2 is pressed, then we're actually stopping the acceleration. It's like a hard brake. So that's what we're doing. And then we're updating all of the interface, the enemies and the player and things, and we're looping all the way back up here. Of course, the draw and move is common multi-platform code, so that's in the multi-platform script. It's not platform specific. When we clear the screen, we're just clearing all of the VRAM from C and 5 zeros here in hexadecimal, and the screen on this system is rather odd. It's 256 by 256, but each pixel is represented by a word, even though it's only a single half byte. So we're actually multiplying 1024 by 256, and that's the amount of memory we need to clear. Here's our character printing routines. We've got a print space routine as well. Basically, our font has no characters below 32, so we're subtracting 32. There's 32 bytes per character in the native format, so we're just calculating the offset in the font data for the character we want to show, and then we are getting the X and Y position, and we're using the sprite routines to show that to the screen. Once we've done that, we're moving the X position for the next character along by 1. Now our font is all the way down here. Here's our font, and here is our sprite data. Now you can see it says MSX. That's because it's basically the same format, 1 nibble per color. It's a 16 color system. So that's what we're doing there, and that's how we use that for our fonts. Now, apart from that, we've got our sprite routines, which of course are used by this as well. We've got a blank sprite routine, which will just clear a sprite off the screen, and it does it by loading in the collision program of the object that's being pointed to by A4. If that's over 250, then the object shouldn't be cleared. It's a dead object or an uninitialized one. We'll use the space from the font to remove it from the screen. Get sprite address will calculate the current frame of the sprite. The sprite data is what we saw just below. There's basically 4 different versions for 4 different frames of animation, and each one has 16 sprites in it. So there's 32 bytes per sprite here. You can see when we're multiplying, we're shifting to the left 5 times there, and there's 512 bytes per bank. So we're shifting the sprite frame, which goes from 0 to 3 repeatedly. It does that automatically, and we're shifting that to multiply by 512 here. We're then adding those together, and that calculates the address of the sprite we want to show, and you can see that's used by our sprite routines here. Show sprite will show a sprite directly from a number. Do get sprite object gets the parameters from the current object that's being pointed to by A4. Now all of the objects in the game, the mines, the player, the enemies, the bullets, they all use the same format, and these have offsets for the sprite number and the X and Y position, and they're loaded in from object A4, well, not IX. That's a hangover from the old version of the Z80 version. I've forgotten to change my comments there. Now, once we've got all of the attributes of our object, we calculate the screen position to show it to from the XY position, and then we transfer the bytes of the sprite to the screen here. Now we're loading in a nibble at a time, and we're shifting because, as I said before, even though we're using one nibble per color, there is actually one word per color allocated within the VRAM as it's apparent to the processor. So that's why we're doing that there. And this is the same as the simple series. This is taken from the simple series here, as is this actually, to be honest. When we want to calculate the memory address, as I said, there's 2 bytes per pixel, and also there's 1024 bytes per Y line. So we're taking the X position and multiplying it by 2, the Y position and multiplying it by 1024, and we're adding that to the screen base here. And that will calculate a memory address from an XY position, and that's what we need for our function. We've already discussed this. This is our function to get the joystick. Wait for fire. We'll check this bit here and see if the fire button is pressed. If it is, then we wait for it to be pressed down and wait for it to be released. This is adds to the debouncing routine, and this is used in between levels and things. And while we're doing that, we're also randomizing the random number generator to give some new nice random numbers. Finally, we've got some common code here. This is the multi-platform code. This, if you want to see how all of this works, please see the Z80 version of this tutorial, because basically it was converted. Every function does the same thing, and I don't want to repeat describing what each function does when the code's only slightly different. So please take a look at that if you want to see that. We've got Chibi Sound, which was in the platform specific series, and this was taken, and I think this was as well taken from the Grime Z80 program I wrote in the past. And that's really all there is to it. So you can see here that with a few bits of platform specific code, we've been able to port this game fairly quickly to the x68000. Now that's all we're going to be covering today. We are going to come back to the x68000 later on with the YQuest, because I actually converted this to work with hardware sprites. Now on a system like the Genesis, where I was using the tile map for the basic graphics, that makes a big difference to the smoothness of the movement. On the x68000 it doesn't make much difference at all. I don't think it makes any difference really, but there is one important reason for doing that, and that's because there's very little, if any, documentation on the sprites, the hardware sprites of the x68000 on the internet, because the only documentation I could find was in a Japanese book, which was in Japanese, and I can read Japanese, so I tried to convert it, tried to translate it and get it working, and I managed it in the end. So I thought it was worth converting this again, even though the hardware sprites don't really improve this game, but it's worth knowing about them and seeing them in action. So if you want to see more x68000, please like and subscribe, and you'll see that coming later on. But whatever you do, I wish you all your best with the programming. Go to my website, you can get the source code for today's example. Thanks for watching today, and goodbye.